Alright, welcome back to video 2 of Unit 10, and we are talking about solids and liquids. So, at the end of the last video, I asked you to think about these two molecules and decide which had stronger intermolecular forces. I hope you determined it was water, but why? Let's think about it. N2, or nitrogen gas, is only going to exhibit London dispersion forces, which, if you recall, are the forces caused by moving electrons. Water, on the other hand, could have some of those dispersion forces, but it's also going to have hydrogen bonding. So it has to be stronger because hydrogen bonding is the strongest. Another concept check for you. So it says to draw the two Lewis structures, but I left them on your sheet. These two Lewis structures have the same empirical formula, C2H6O. We want to know about the boiling point of these guys. Well, let's think about it. On the left, we have ethyl alcohol, or ethanol, and on the right, we have dimethyl ether. You'll learn how to name these soon. So on the left, this guy actually is going to exhibit a little bit of hydrogen bonding. Why? Because that oxygen right there is going to attract other hydrogens to attach to him. You might say the guy on the right would do the same thing, but in actuality, he's kind of protected by those 4 hydrogens around him, whereas the other oxygen only has the 3 hydrogens. So the oxygen on the right over here, he's kind of protected, versus this guy on the left that's free to participate in some hydrogen bonding. But what kind of forces could occur over here? Well, we have 2 dipoles, so we could have some dipole-dipole forces. We could have some electron dispersion. Does any of that matter if this guy has hydrogen bonding? No, because it's the strongest. So our boiling point is directly related to that. And our ethyl alcohol on the left will have a higher boiling point than the dimethyl ether on the right, because he has hydrogen bonding. Okay, so let's talk about some characteristics of liquids. When we say they have low compressibility, we mean that we really can't put a whole lot of pressure on them or compress them, partially because they aren't rigid and they have a high density compared to gases. When we think about surface tension, it's like when you see those bugs that stand on the water. Why can they do that? Well, it has a lot to do with physics, but essentially it's because that surface area of the bug's feet is not big enough to really make an impact on that water or that liquid. So liquids with these large intermolecular forces have high surface tensions. That's why water can hold those bugs up. But let's say that bug was standing on alcohol, which has a lower surface tension. He might not be able to stand on it as easily. He might sink into the alcohol. Viscosity, we already know about this. That's resistance to flow. But in the past, we've only thought about that in relationship to density, and we really need to think about it in relationship to these intermolecular forces. Something that's really viscous is attracted to itself, and inside that liquid, it's hard for it to flow and want to move apart. So those high intermolecular forces can lead to something being very viscous. In addition to that, we have what we call capillary action. Well, if you think about capillary, you might think about your body. You have capillaries in your body. If you've ever broken a capillary in your eye, you get the little red lines. It's essentially a narrow tube that holds a liquid. So capillary action is what we call the spontaneous rising of a liquid in a narrow tube, and it depends on 2 things. The first is what we call cohesive forces. Well, if someone's cohesive, they work together well. So when we think about cohesive, we're going to think about intermolecular forces. So we're thinking about hydrogen bonding, dispersion, and why am I blanking? Dipole forces. All of those things. We also have to think about adhesive forces. This has to do with what the liquid is held in. So cohesive means within the actual liquid, what's happening with the molecules, and adhesive means between the liquid and its container. So the reason capillary action works is because it causes an increase in the surface area, and these cohesive forces oppose that, so it moves up the tube or down the tube, depending on the type of capillary action we're talking about. So here's a good picture to demonstrate. What I'm showing on the left is water, and what it's creating is what we call a concave meniscus, which means that it goes down. This is happening because the side of the glass or plastic or whatever the tube is made of is actually attracting those water molecules, and it's just an attraction because of the polarity of water. Now, it wants to hang out by the side of our container. That's why sometimes when we're using a burette, like we use for titrations, you'll see the drops stuck at the top. You can't get them to move down the tube because they're actually pretty attracted to the side of the tube. Because of that, we get this great meniscus that we always read to the bottom of. You could always practice and see what you think the volume is on that guy. And if you said it was about 5.55, guess what? You're wrong. It's about 4.41, 42, something like that. Remember, we read from the bottom up in a meniscus. And on the right here, what we have is some mercury. What's happening with the mercury is it's creating the opposite effect of the meniscus. So this one is up like this because he's having the opposite effect. He doesn't want to be attracted to the side, so he's pulling away from the side of the container versus the water pulling toward it. So this is a good one because they're a little closer. Concave versus convex. Well, mercury's nonpolar because it's just mercury hanging out with itself. It doesn't have any of those attractive forces. That's why it causes that to occur. So its forces are more cohesive than adhesive. So we get this convex meniscus, which is kind of cool. If you look inside a thermometer, you'll see that. Okay, so how about solids? We technically have two types of solids here. The first being what we call an amorphous solid. This means it has disorder in its structure. In other words, it's not perfect throughout. So if you think about glass, sometimes you can see an imperfection in there. That's because it's an amorphous solid. On the other hand, we have a crystalline solid. This is a very organized and ordered structure, and we have talked about what we call these, which is lattice. Think about a lattice fence. It's a three-dimensional system that has designated points where the lattice meets, and this is what makes up our crystal. And what we call the inside of our crystalline solid is a unit cell, and that refers to the smallest repeating unit in the lattice. So think about your lattice fence. When you see all those little crisscrosses, one crisscrossed area is like the unit cell. So there are a couple different ways we can refer to these unit cells, but this is a good diagram because it shows one simple cube here. And in my diagram here, I have like 8 cubes stacked up. This is the lattice. This is the unit cell. This is a little bit more fancy cube, has more points in there. Well, when we put a bunch of them together, here's what our lattice looks like. And then we have what we call our face-centered cubic. Tons of molecules packed into that area, but that's still our one unit cell that's making our cube. And there's a bunch stacked together. Now our 3 examples here are polonium. And if you really kind of look at this guy, you can see that there's a couple of them stacked up from the edges. So we actually have 1, 2, 3, 4, 5, 6, 7, 8 that are like a quarter of an entire atom. But on this one, there's a big atom in the middle, and then we have 8 on the outside that are quarter atoms. That's a good example in uranium. How about gold? Really tightly packed. Looks like we have 4 halves and 8 quarters. Well, which of these would be stronger? Gold. Look how tightly packed it is. So that's how we're thinking about our lattices. Now, we talked about this a little bit a couple chapters ago, but when we analyze a solid with X-ray analysis, we're figuring out the structure, and we're using diffraction, which is when these beams of light can't pass through, so they end up changing direction. If it's constructive interference, that means we have these parallel beams that are building up to make a bigger beam. If it's destructive, they're tearing each other down or they're interfering with one another, like when you're trying to tune into a radio station and it's not working. It's destructive waves. What we can do with this is we can look at an area of light and dark patterns and interpret what we think the metal is or the crystal is or just what the substance is in general. We kind of did this when we were doing our lab over in Miss Johnson's room, and you looked through your microscope. Very similar to what we were doing. Okay, so here's a little equation here. You don't actually have to know the equation, but you have to understand what's going into it. So n here is representing any integer, and just like before, our crazy symbol there is representing wavelength, our d is distance, and our little o with a line, omega, what's that represent in math, is angle. So what we're taking into account to figure out how something's structured is the wavelength, the distance between the atoms, and this angle. So if I'm able to measure my wavelength and my angle of deflection or reflection, I can figure out the distance between atoms, and that's really important to understanding the strength of special alloys or crystals. It can just be super important in science. So here's an example of how we can use it. We have these x-rays, they have this wavelength of 1.54A, and we analyzed an aluminum crystal with it. It gives us our reflection angle, and it gives us our N. Calculate the distance between the planes of the atoms producing this reflection. It says in picometers. So what we're going to do here is just plug into our equation. Our 1.54 was on the left because that is our wavelength, and our N would be 1, so we left it out of the equation here. Our 2D stays on the right, and we take the sine of the angle given. Plug it all in, rearrange, you're going to end up coming out with 2.33A. which is right here. There's our answer. But it said in picometers, so what we did was convert over. Well, that's not something we've really talked about yet, but 1 times 10 to the 10th A equals 1 times 10 to the 12th PM, so we come out with 233 picometers. I don't think you really need to know this conversion, but you need to understand how we figure out the distance between them, and to do that we use wavelength, and we use deflection or reflection angles. So let's talk a little bit about the types of crystalline solids. We already know about ionic solids. These are the ions that are at the points of the lattice that describe the structure of the solid. So think of a salt crystal. If we zoomed in on that salt crystal, we could identify the sodium, we could identify the chlorine, we could identify the ions within. If we zoom in on something that's covalently bonded, like sugar or sucrose, we could identify certain parts of that as well. It's a little harder to identify. Why? Well, it's got carbon, hydrogen, and oxygen, which are actually fairly small compared to something like sodium and chlorine, so it's harder to identify, but we can still do it. And lastly, we have what we call atomic solids. And these are the ones that are from the periodic table. And we can look at it and say, okay, that's carbon. This is a diamond we're looking at, or this is graphite. It definitely has carbon in there. So these are good ways to identify different crystals. Okay, so within atomic solids, there are 3 types. And the first one here is what we call a metallic solid. I think it's really funny that the book defines it as covalent, because if it's 2 metals, is it covalent? No. What they're saying is it's going to be nonpolar because we have the same metal mixed throughout. And we already know that we think of metals as having a sea of electrons, so we're thinking about these as if they're nonpolar covalent bonds when we really know they're these special bonds that are between metals. Then we have our network solids. This is when we have a whole bunch of covalent bonds that lead to this giant, really complex molecule, and a diamond's a perfect example of that. If you remember me showing you the structure of a diamond, you remember how complex those molecules were. And we also have what we call group 18 solids. But hold on, group 18 doesn't bond. Guess what? It does hang out with each other, and I'm going to go into that a little bit more in my next video.